Hello, we are going to make a network of blowing nozzles, which is shown here. We have a blowing air supply with a length of 4000, one bend, a bifurcation for the first nozzle, a bifurcation for the second nozzle, third nozzle, fourth nozzle, with dimensions here. We are therefore going to model this small network. The pipe diameter is given here in inches. It is 6 inches, so we are going to do a conversion. So 152.4 millimeters. We are therefore going to create a pipe with a diameter of 152.4 millimeters. And save this pipe in our library. We see our pipe in the pipe elements, here 152.4 millimeters. We drag and drop this pipe diameter in the interface, and thus create a new network. Our diagram gives us a first length of 4000 millimeters. We adjust the length in meter, 4 meters. Then we have an elbow and a meter of pipe. We use the function continue after elements. The size of the grid being 1 meter. So here we have an elbow and a meter. Then here at 1 meter we have a bifurcation. So we are going to insert a bifurcation. A 90 degrees. We are going to orient the fitting correctly. So here we have to go up a meter. We are going to adjust this branch and make it go up a meter. Here, OK. And this branch there, being straight, we will also adjust it and bring it up there. Once we have already set our position, to avoid selecting points with the cursor, just press the space key. At the bottom, an indication selection off warns you that you can move on the screen without selecting a point or modifying the orientation of the element being adjusted. This is useful when the screen is loaded with many elements. And we click on OK. Here is our first part. We continue. Here, we have doubled circulation. This one will rise by 0.4. We will create our bifurcation here. We will now adjust the two branches. Adjust the element, we make it rise at 90 degrees. And set its length to 0.4. And we validate. We continue. On the diagram we see a length of 2 meters between the two nozzles. So we are going to adjust and apply 2 meters. 1 meter, 2 meters, and we validate. There we go up, bifurcation at 0.4. Create a separation. Adjust. We go up vertically and set the length to 0.4. And we validate. Here, same thing. We adjust the positioning. We recenter the grid, selecting the starting point of the pipe element, and select the point at 1 meter. And we are going to press the Enter keyboard key because we are going to continue after. When we press the Enter key on the keyboard, in the adjustment phase, this corresponds to validate and continue after. Now we want to go up from 1 meter. We continue, enter key, the diagram goes up 1 meter, an elbow, then 1 meter. Another elbow, and back 1 meter here. 1 meter here. We zoom the screen. We select the point at the beginning of the conduit. To recenter the grid and have a point at 1 meter here. And we validate. So here is our network taking shape. We're going to do the same thing here, 1 meter and 1 meter back here. Continues after the element, 1 meter here, we press the enter key. Or else click on validate and continue, it amounts to the same thing. And there, we will click on validate to finish. We have a small return of 0.1 meter. And here, we have a small return of 0.4 meters. We will make the return of 0.1 meter. Continue after. .1 meter, it's too short to build, with rounded bend. So we will adjust the length to 0.2 meter. Here it is, same. Here it is, same thing, continue after. So we will give the direction by selecting the grid point here. And the length of 0.2 meters. Otherwise, it will not pass at the level of the radius of the elbow. You should put a sharp bend, but in this demonstration exercise, we won't worry about the precise dimensions. From here we have a return 0.4 meters down. Continue after element. Orient downwards. Set the length to 0.4 meters, validate. Same thing here, continue after, we are going to go down. That's it. We press the spacebar to deactivate the selection of points. And we enter 0.4 meters here. Here is our system with our nozzles. We now have to model our nozzles. To determine the diameter of our nozzles, we only have the desired speed at the nozzle outlet. We are going to use the volume flow rate at the fan, which is given to us in the specifications. And we will divide this overall volume flow by the number of nozzles to obtain the average flow per nozzle, and adjust the nozzle outlet section to obtain the speed requested at the nozzle outlet. We want 500 kilometers per hour, we will speak in meters per second. We will open the unit converter, 500 kilometers per hour gives us 138 meters per second. So we are going to set a target of 140 meters per second at the exit of the nozzle. We will write down our data. We have an overall flow of 6,000 cubic meters per hour. Divided by 4 nozzles, this gives us 1,500 cubic meters per hour per nozzle. We are going to do a conversion in cubic meters per second, that gives us 0.416 cubic meters per second. This is the flow that a nozzle must provide. Knowing this flow rate and the desired output speed, 500 kilometers per hour, therefore 138 meters per second, We round up to 140 meters per second. The speed is equal to the flow divided by the section. We can say that the section is flow divided by speed, 0.416 cubic meters per second, therefore divided by 140 meters per second, gives us a section of 0.00297 square meters, which is 2,970 square millimeter. So we need a section of 2,970 square millimeter. If we want to produce the speed of 140 meters per second with a flow rate of 0.416 cubic meters per second, this gives in theory a nozzle outlet diameter of 61 millimeters. But let's choose here, for example, 54 millimeters of nozzle outlet section. We will therefore create 54 millimeters nozzles. We select the pipe, and use the shrink function, and we set our outlet diameter to 54 millimeters. Insert cone. We will now copy this cone, copy, and paste here. Paste. Downstream. We can also select the end, and use the Ctrl and V keys. And here are our nozzles installed. We create a flow generator. We will force the flow test to 6,000 cubic meters per hour. We check the flow before going to get the precise operating flow. Because it is not obvious that the fan can provide the requested pressure. So for now, we're just going to see if the nozzle distribution is correct. At the nozzles, we have 183, 180, 179 meters seconds. We're going a little too fast, so we're going to make the nozzle exit sections bigger. I remove the nozzles and start shrinking again. I use the shrink function, and we set the output to diameter 60 millimeters. Keyboard key Ctrl and C to copy the nozzle, keyboard key Ctrl and V to paste the nozzle. And I restart a simulation at the flow rate of 6,000 cubic meters per hour. Here it is in about 148 meters per second. We wanted 140 meters per second, so we'll leave it at that. In terms of balancing, we are quite well balanced. We have speeds that are roughly equivalent everywhere. From 148 to 146 meters per second. We don't have too much speed delta between the nozzles. So the configuration seems correct. Now we have to check if the generator proposed in the specifications can provide the pressure that is necessary to generate this flow. We are going to create a pressure generator. We are going to use, in the library, the pressure generator editor, and we are going to enter the pressure curve. There are also possibilities to enter NPSH and yield values. We are going to select, for our ventilator, the delta P Pascal option. So that means we're in gas, the NPSH is no longer displayed. We are going to open here, the technical sheet of the generator. And we are going to enter the curve points of this generator. We have to provide data from scratch. We estimate that the pressure at 0 will be 20,000. We need 6 points. We will go from 0 to 2,000 cubic meters per hour. (4,000 cubic meters per hour), 6,000 cubic meters per hour, 8,000 cubic meters per hour, 10,000 cubic meters per hour. We enter the corresponding pressures. At 0 cubic meters per hour, we have a pressure of around 20,000 pascals. At 2,000 cubic meters, we are at 21,000. At 4,000 cubic meters per hour, we are around 22,000. At 6,000 cubic meters per hour, we are at 21,000. At 8,000 cubic meters, we go down to 19,000 pascals. And at 10,000 cubic meters hours, we estimate the pressure at 15,000 pascals. Here, we can enter the yield curve. This will tell us the yield of our system. So in yield, here we have a yield of 25%. So, if we follow the curve, at 0 cubic meters, of course, the yield is 0. At 2,000 cubic meters hour, we will have a yield of 30%. At 4,000 cubic meters hour, we have a yield of 50%. At 6,000 cubic meters hour, we have a yield of 60%. At 8,000 cubic meters hour, we have a yield of 70%. Same thing for 10,000 cubic meters hour. Then the name is FNC centrifugal fan. Diameter 152.4. We will use the generator curve as an image. Our fan is fully defined. The generator, FC centrifugal fan, has been recorded in our library. We are going to close this editor. And now, we are going to test our system with this fan. The theoretical fan for the 6,000 cubic meter hour test, we are going to destroy it. We go to our library, select the centrifugal fan, to drag and drop it into the network. The location of the generator insert is undetermined. Do you want to insert this generator at the beginning of the network? Yes. Our fan is inserted at the start of the network. We will test this fan and find its operating point by clicking on refresh. I made a big mistake. I tested with water. So the first thing to do, excuse me, is to select the circulating fluid. Which is air, at 20 degrees. Use this fluid for the calculation of the density according to the altitude. Click yes, we will give the altitude. We will say that we are at an altitude of 100 meters. Okay, so our fluid has been configured. We are going to launch the calculation of the operating flow. We obtain a fluid flow of 6,106 cubic meters per hour. This is very close to our need in the middle of performance. The speed at the nozzle outlet is 150 meters seconds. With this fan, we're well positioned in the performance curve. We're going to color by pressure, and we're running test rides with 1,000 particles. Click on trip test. At 500 kilometers per hour, you can't see the particles coming out. We're going to remove the culling. We're going to run the test again. We're going to slow down. So, the ejection velocity being very fast, it is difficult to see the particles coming out. So that's it for this tutorial. creating a blowing network, with nozzles in operation, specifications, and a fan.